Hey folks, we're starting in on Unit A, Analysis of Variance. We're at the midpoint in the course. This particular unit is a really important one. It's also probably the most difficult one to both get your head around and also the calculations. So hang in there, but there's a lot of stuff in this particular unit here that we want to go through. And I'm going to be introducing you to a number of different tests here. I want to go back here just a few pages to the beginning of Unit I, and I showed you with the test of independence here, right at the bottom here, I was talking about the types of variables that we have. So there's nominal variables, there's ordinal variables, and there's interval variables. And in 307, we're looking at how they interact with each other, and in particular, how they vary with each other. So if it's two nominal variables, then we would use a test of independence. But if we have one nominal and then one interval variable, or later we'll see it could be an ordinal variable, then we're talking about something called analysis of variance. So, or ANOVA. That's where analysis of variance, or that's where ANOVA comes from, is analysis of variance. And then again, the last part that we'll be looking at here is when we've got interval versus interval, then we'll be looking at regression. But right now, we're taking a look at this area right here, which is ANOVA, and we'll be looking at a number of different tests on that one. I want to also take you to the bottom of the manual here. So this is going to about page 214 or so. So this is after all of the formulas here. This is part of your formula book. And then I've got these sideways pages here for when you're comparing two variables here. Now, what I've actually done here is I've rotated these in my particular manual so they're a little easier to use. So I've rotated these guys, and then there's these guys here, which are the critical values and p-values pages. And then down here, we're going to be looking at the F table today. And so I've rotated them. So you won't see this in your book, but I've rotated them in mine so that they're all down here. So here's the F table, which we'll be taking a look at, and there's actually two of them, depending on what your alpha is. But this is the one that I wanted to just stop at for a moment. So this is the one that's talking about when you've got two variables that you are comparing, what test should you use? And so what we've got here is, again, if we've got two nominal variables, then we're using a test of independence. If we've got nominal versus ordinal or nominal versus interval, then these are all in the ANOVA classification here. The nominal versus ordinal has something called the Kruskal-Wallis test, which we'll be introduced to, which is just a type of ANOVA. And then we'll be getting into the last part here, which is really regression. So that's talking about interval versus interval, or if one or both of those is ordinal. So those are the main types of interactions that we have here. And we're taking a look at this part right here. Now, what we'll see here is when we're talking about nominal versus interval or nominal versus ordinal, then we're talking about this area right here. And so there's some further pages to take you through that will help you decide which test is the one to use here. Okay. And then I've just rotated the critical values and p-values pages down here, so you'll see them. So let's get back here then. And we're going to start here then on analysis of variance. And so again, this is where we've got a nominal variable versus an interval variable, or later we'll see it could be an ordinal variable. Okay, so nominal variable could be something like, what program are you in? And so we might have 3 or 4 DSB programs that we're looking at. And then we might have an interval variable such as, well, how many hours do you spend studying per week? So that's nominal versus interval. And we would say, well, that's a candidate then for ANOVA. And there's certain conditions that need to occur for it to be a proper ANOVA test, but we'll take a look at those as we go through here. So that's what we're looking at here then. We will specifically be looking at a bunch of different topics here. So we'll start with actually a new distribution, and this will be your last distribution that you'll be introduced to in your first 2 stats courses, so the F distribution. And then we'll take a look at something called the one-way ANOVA test with its multiple comparison of means. The two-way ANOVA test, we're not going to go into actually any calculations. I'm just going to refer to you on that one. And then we are going to talk about some assumptions, and well, that will lead us to the Kruskal-Wallis test and the Friedman's test, and then some pages at the end here about how to do ANOVA using Excel, which is actually pretty easy. So let's jump in here, and I'm going to introduce you to something called the F distribution. Now, if you remember in the Unit V, remember we did this kind of thing here, where we were testing that sigma squared, or it could be just sigma, is equal to some number, k. So a k could be 10 or 100 or something. So we were testing that the variance is equal to some amount. In an F test, what we're doing is we're actually comparing 2 variances. So it's used to test if a variance of one population equals the variance of another, or like this. So in this particular one, we use a chi-square test. In this one, we use an F test. And an F test is actually just really a ratio of chi-square distributions. And you don't have to remember that, but that's where it actually comes from mathematically. So let me give you an example of what that would look like. We're going to go through a simple F test problem, and you'll see that it's actually pretty easy. Are the variances in ages of students at RDC and U of A the same? And so to answer this question, we're going to take 25 students from RDC. So that's going to be the N of RDC. I'll just put a little subscript here. And 41 students from U of A. So that'll be the N for U of A. And what we end up with is sample variances of, so this would be an S squared value for RDC. And this will be an S squared value, a sample variance for U of A. And we're going to use an alpha of 10%. All right. The test looks like this. Step number 1, of course, is always the same, your HO and your HA. So in this case then, we've got that the variances are equal versus the alternative that they're not equal. Of course, this could be a one-sided test. If we are testing, let's say, we're testing a hypothesis that RDC variances are higher than U of A's, but in this particular case, we're just asking if they're the same. So it is a two-sided test. The test statistic is really simple. It is just simply F star is equal to the ratio of the 2 variances. So the sample variance of RDC over the sample variance of U of A. Now, what we've got here is if these 2 are equal, then we would expect something equal to 1. So we're really interested in if that number is significantly different from 1. So if the variance for RDC students is much higher than for U of A students, then we would have a large F star value. On the other hand, if U of A is much larger than RDC, then we would have a small fraction. It would be close to 0, right? So that's what we're looking at. It can't go below 0 in this particular case. So just like a chi-square distribution, because we're talking about a ratio of variances here. But 1 is when they're equal to each other. So very high or very low would cause us to reject HO in that particular case then. So a couple things about the F distribution. It's that it's actually similar in shape to chi-square distribution. And it has a lower bound of 0, just like a chi-square distribution, because it's a ratio of variances. Theoretically, no upper bound, but it's skewed. It's skewed to the right. So we actually draw it the same way as a chi-square distribution. Now, if the sample variance is much larger, we've just talked about this. So really, we're looking at how close the variances are to 0. All right. Let's talk about how you read the chi-square table. So just like at the beginning of Unit V, we were introduced to the chi-square distribution of the table. Here we're going to be introduced to the F distribution. Sorry, I said chi-square, but the F distribution. So we want to talk about how to read the F table here. All right, now, the way that you do that then is it's important to know here that we have degrees of freedom for both the samples. So we have degrees of freedom for the numerator and degrees of freedom for the denominator. If we go back to this particular example here, what we have in the numerator here is RDC, and so its degrees of freedom are going to be the n of RDC minus 1. And then for U of A, of course, U of A is in the denominator, and so its degrees of freedom will be the n for U of A minus 1. So there's actually two sets of degrees of freedom, whereas when we were dealing with t distributions and with chi-square distributions earlier, we only had one set of degrees of freedom here. Okay, so what you do here then is, well, let's actually just take a look here at the tables at the very end here. So I'm going to go to about, well, let's actually go here to chi-square. I'm just going to back up here. So here's a normal table, and remember what we did with the t table is we said that we've got degrees of freedom, so each row has degrees of freedom, and so we chose certain percentages which are the common alphas or alpha over 2's. And so we have 1, 2, 3, 4, 5 different columns here. And then we actually doubled that number of columns because with a chi-square distribution you have areas in the right-hand tail, areas in the left-hand tail. You don't have 0 in the middle like you have with the t distribution, and it's not symmetric. So we actually had to have two sets of columns. What we've got here, though, is just one set of degrees of freedom. And when we're talking about the F table, which is down here, now I'm going to go actually down a few more pages here where I've flipped it right here. So right there. So I just rotated those. What we've got here is you've got degrees of freedom for the numerator and then degrees of freedom for the denominator. So you can see that there's all sorts of combinations here. And if we tried to have a 0.5% column, a 1% column, a 2.5% column, a 5% column, and a 10% column, which is what we had for a chi-square distribution, that table, and also for the t table, then you'd end up with a real mess here. So what we do actually is we say, well, you know, the common alphas are 5% and 1%. And so what we have is a 5% table and a 1% table. And then we find the degrees of freedom for the numerator, the degrees of freedom for the denominator, and that gives us the critical value for an F distribution. That's how we do it. So let's go back here then. By the way, I'm just going to plug in my iPad here. There we go. So let's go back to where we were then. And that's on about there or so. So to find the upper tail value, so if we took a look at this particular example here, you'll see that this is a two-sided test. And so what we would do in this particular case then is we would have, to calculate a critical value, we would have something that looks like this. So we would have the degrees of freedom for the numerator, which is RDC, minus 1, and then the degrees of freedom for U of A, which is the n minus 1 for U of A. And what we've got in the middle is 1, or it's pretty close to 1 anyways. It's actually got a bit of a goofy formula here. But if this is a two-sided test, which is what it is, we would put alpha over 2 here, and we would put alpha over 2 here. And so we want to find out what are those critical values. Now, if we're using an alpha of 10%, then this would be 5% in each tail. So we need to go to the 5% column and then find the degrees of freedom. And the degrees of freedom in this particular case then are, what do we've got here? 25 minus 1, so it would be 24 for the numerator. And then we've got 41 minus 1 is 40 for the denominator. Okay, so let's go down here, and it says, step number 1, turn to either the 5% or the 1% table, depending on the level of alpha, or in this case, alpha over 2. Calculate the degrees of freedom for the numerator, and they're going to be n minus 1, so in this case is 24 for RDC. Calculate the degrees of freedom for the denominator. So U of A's is 41 minus 1 is 40. And that tells you the column and the row to use. The intersection of the column and the row gives you your upper tail critical value. Let's go find that guy there. So we're going to go back down here to about there or so. Okay. And so we've got the degrees of freedom for the numerator was 24. The degrees of freedom for the denominator was 40. So we just have to find out where those intersect. And we're going to find it's right there, 1.79. Okay. That's the guy, whoops, right there is the intersection of 24 and 40. And that's for an alpha over 2 in our case of 5%. So that is our upper tail value. Let's go down back there. Now, the lower tail value, it's just a little goofy here. So what you need to do here is you turn to the 5% or the 1% table. You calculate the degrees of freedom as in steps 2 and above. So we've got 24 for RDC and 40 for U of A. But then what you do is you reverse them. And you find the number that corresponds to the table of, so the row becomes the column and the column becomes the row. You find the number, and then what you do is you invert it. So you take 1 over that number. So you take the inverse of that number. So let's take a look at that. That's going to be, we're going to go down here to page 225. So what we do is, instead of looking at 24 and 40, we look at 40 and 24. So in this case then, 40 down here, and then we've got 24 here, and that's going to be 1.89. And then what we do is we take the inverse of that. So it would be 1 over 1.89. Okay, let's go and summarize all that. Oops, I went, there we go. Okay. So find the critical values for the RDC U of A example. And I'm just going to reproduce what we've got there. So we had an F of 24 and 40, right? We've got 1 in the middle here. We've actually got a 0 down here. And we're looking for these values right there. So 5% and 5% here. All right, so when we went to find that upper value right here, that came to 1.79. And then this guy right here will be 1 over 1.89. And that's 0.53. It's always good to just do a real quick check to see if those numbers make sense. So we've got 0 down here, and then we've got 0.53, we've got 1 in the middle, and 1.79 up there. So they're all in order like that. So what we've got here then is we would say if your f star is less than 0.53, or if it's greater than 1.79, then we would reject HO. So that would be really step number 3. That's the critical values. Step 4 is where we actually go now and do the calculation. And we've got, going back to the problem here, we had 13.5 and 7.5 are the two variances. So f star is equal to the variance for RDC over the variance for U of A. So 13.5 divided by 7.5, and that gives us 1.8. And what you can see here is that 1.8 is just tucked in there. So it actually is significant. So what we've got is 1.8 is greater than 1.79, and therefore we would reject HO. And what that's telling us then is that this is saying that RDC students have a significantly higher variance in ages of U of A students than U of A students. So that's where we're going to end this one. We're going to then use the F-test in a very specialized kind of problem called the one-way ANOVA test. So that's the next thing that we'll look at. And we're going to end the lesson here. Thanks for watching.